All right, let's do an example here. Let's say that you have a bullet made of lead, mass m, going some initial velocity v. It hits a target and stops in it. Okay, if the initial temperature of the bullet was 20 degrees Celsius, the question is how fast would it have to be going so when it stops, it melts? Okay, so we make a couple of assumptions here. We're going to assume that all the kinetic energy is not created or destroyed, so when it stops, we're going to assume that the target doesn't move, so we do not transfer a lot of energy to the target. We're going to assume that the target's pretty well insulating, so not much of the thermal energy goes into the target, and so most of the energy stays with the bullet. So these are not perfect assumptions, but it does make the math easier. And so we're going to assume that all the kinetic energy, 1/2 mv squared, became thermal energy. Okay, well, what happened? Well, two things happened. We had to heat this up to the melting point. So that is the energy going into changing the temperature, and then we had to melt it. Just getting to the melting point doesn't change it, so we have to include the temperature of melting. So this is heating it up, and this is melting it. Okay, and so that's what we have here. So 1/2 mv squared equals mc delta t plus mLF. The m's cancel, so we do a little bit of algebra. And so v is going to be the square root of 2 times c delta t plus latent heat diffusing. So we need several things here. We need to know the specific heat of lead. Okay, so how do we do that? Well, the options are either memorize the properties of every known substance or you look it up. And so you look it up. And so that's going to be that's going to be equal to 129 joule per kilogram Celsius degree. We need to know the latent heat diffusion of lead. Again, something you look up. So that's going to be 2.32 times 10 to the 4th joule per kilogram. We need to know delta T. So delta T is going to be the melting temperature minus my initial temperature. So we need to look up the melting temperature. So the melting temperature of lead is 328 degrees Celsius. So that means that delta T be 328 degrees Celsius minus 20 degrees Celsius. So that's 308 degrees. Okay, plug all those numbers in. Okay, so that's square root of 2 times C delta T plus L sub F. We plug in all the numbers and we come up with 293 meters per second. Okay, so that is a perfectly achievable velocity for a bullet. And so that means it's possible to have a lead bullet, so it's unclad, bullet, just a pure lead slug, and it hits a target and then melts. Okay, now that assumes several things. It assumes the target, we do not transfer energy to moving the target, and it assumes that very little of the bullet's thermal energy goes into heating the target. So those are not perfect assumptions. So in reality, the velocity would have to be a little bit higher than that. But again, that's a perfectly reasonable velocity for achieving with a bullet. And of course, they actually make bullets designed to do this. They actually have bullets in which the bullet is got a little bit of copper cladding on here. They're hollow point, so they flatten out and they stop real quickly in the target, and the partial cladding actually chops up the lead into little bits which disperse and make a cone of molten lead inside of the target. And these are anti-personnel rounds, and they are actually available. So they actually do make bullets that use this kind of physics.